Three gears are arranged as shown in the figure. Find angle theta. Okay, so we've got these three gears shown here. They're meshed this way. And we want to solve for this angle theta, where you've got this line connecting the two centers of these two gears and the two centers of these two gears. And so there's an angle between those two lines. So how can we solve for this angle? Well, we can solve a triangle. We can set up this triangle here. And if we have enough information about the triangle in terms of certain angles and lengths, then we can solve the triangle. We're not trying to find all of the triangle values. We're trying to find just this one value, but in essence, that's what we're doing. We might not need this length here, but if we solve the triangle, then we've solved for this angle. Okay, so we can see that somehow we have this angle here, the angle between the line connecting these two, the centers of these two gears and the centers of these two gears. The angle made between those two lines is 38 degrees. We don't have any other angle, but we can figure out this side length and this side length, because this side length is going to be the radius of this gear plus the radius of this gear. And same with this side length, the radius of this gear plus the radius of this gear. So this, we can see that, so we have 2.7 and 1.6. So 2.7 plus 1.6, 7 plus 6 is 13, 4.3. So this is 4.3. And then here, 1.6 plus 3.6 is 5.2. So we've got two side lengths and an angle. And now we've only talked about, we were introduced to the law of sines in this section. And we discussed that there's two cases where you can use the law of sines, the straightforward non-ambiguous case and the ambiguous case. But we can see here that this is actually not the straightforward case where you've got two angles and a side length. In this case, we've got two side lengths and an angle, and actually the angle that we have is not included between the two side lengths. If it was, that would be something that we would use the law of cosines for, which we haven't learned yet. But this is the ambiguous case of the law of sines here. When we have two side lengths and an angle that's not included between the two side lengths. But the only issue is we didn't really get into the ambiguous case. That's something I was telling you we're going to really look at in the next section. So, and we actually didn't even work any example problems in this section using the ambiguous case. So I'm really not exactly sure why they gave a problem like this in section 1. I think the reason, I honestly think the reason is because, okay, if we go ahead and work this out, let's go ahead and try and work this out. So, all right, we know the law of sines is the ratios between the sine of an angle and the side length opposite that angle, that's constant over the entire triangle. So if we can say the sine of 38 over 52, okay? And now we can do let's label these angles. So this would be angle A. We're trying to solve for angle A. This would be angle B. This would be angle C. Okay, so we need to go ahead and solve for angle C. So that's all we can do, because we don't have, if we had this side length, we'd go ahead and use it and get theta, but we can't do that yet. Now over 4.3. Okay, so we've got, let's see, 52 sine of C is equal to 4.3 sine of 38. So sine of C is equal to 4.3 sine of 38 over, not 52, 5.2. 5.2. Okay, so 4.3 times sine 38 divided by 5.2 is 0.509105. Okay, now we take the inverse sine of both sides, and we get that angle C is equal to the inverse sine of 0.509105. All right, but we know that since we introduced this inverse sine to solve an equation, we have to think about all of the possibilities. Like, it's the same idea with the square root or the principal even root. If you just have, we talked about this with inverse trig functions. If you just have this, the principal root of 4, that's equal to 2. But if you introduce this principal root to solve an equation, you have to put the plus or minus, right? It's the same idea here. So this is why it's the ambiguous case, because we have to think about what are all of the potential angles that when you take their sine, you get this value. So, but why do we even consider the ambiguous case? If we're going to have an infinite number of possibilities, right? Because that's what we know when we were solving inverse trig functions. We know that what would happen is it would come out with an infinite number of possibilities, possible angles that satisfy the question. Well, this is different because when we're solving a triangle, the angle can't be a negative angle, so that eliminates all possible negative angles. And it's not going to be an angle greater than 360, so it eliminates all of those angles. So in reality, it's going to come down to, most of the time, it'll just be two possible angles that you have to think about. So it's ambiguous, but we still can use the law of sines to solve it. Worst case scenario, you say, okay, the triangle could be either this triangle or this triangle. One of two possibilities. So we can still kind of solve it. So, okay, let's take the inverse sine of this value here. We're in degree mode. So 30.6 degrees. Now, okay, sine is positive in quadrants 1 and quadrants 2. So there's another angle in quadrant 2 that has this as a reference angle, and that's this angle. So angle C could be one of these two angles. All right. Now, I think the reason why the textbook gives us this problem to work with in this section is because we're going to see in the next section is when it comes to the ambiguous case of the law of sines, there are certain scenarios where it still ends up being one unique triangle anyway. Like the constraints of the system are where, like, if we look at this, so, okay, we know one angle is 38 degrees for sure. So, okay, if the angle was 149.346, okay, let's add 38 degrees to this. Well, that's greater than 180, so it can't be 149.396. It has to be. That means the angle C has to be this. So I think that's why they're giving us this problem, since this technically falls under the ambiguous case, but it's one of the cases which we're going to learn about in the next section where there ends up being actually only one triangle anyway. But that's not always the case. It might be the case where you have to specify, no, there's two potential triangles here. And so the designer or whoever would have to decide which triangle they want to use. Whereas with this case, if you're saying this angle has to be 38 degrees and these are the radiuses, well, then there's only one angle that's going to work here. And so this has to be, angle C has to be 30.6 degrees. Okay? So, but again, we're going to get into full detail on the ambiguous case of the law of sines in the next section. So, okay, so that's angle C. And so, okay, now we're home free. We could just sum the angles to get theta. So we've got this plus 30, and then 180 minus this is going to be that angle. So 119.4 degrees. That's the only angle. That's the only angle that theta could be. There's no ambiguity here. For this triangle to exist with this side length and this side length and this angle C has to be this, and angle theta has to be this. But again, I want to stress that still technically is the ambiguous case of the law of sines, even though the triangle is actually not ambiguous, because we had to still kind of, but with the non-ambiguous cases, with the law of cosines and that one case with the law of sines, Once you've got that, once you establish that you've got, like, for example, two angles and a side length, it's done. There's no ambiguity, 100%. Here, once we had two side lengths and an angle, we didn't know. It might be ambiguous, it might not. So it's still, in that sense, it's still considered the ambiguous case of the law of sines. Okay, wait, I messed something up here. So, okay, we have this angle plus 38. I added 30, yeah, so this is angle C, is this, has to be this, plus 38, and then 180 minus that. 111.4. So for some reason I added 30. I don't know why I did that. So 111.4.